Good day, I'm Norman Wildberger. Today we're finishing off this little series called Relativistic Velocity Addition, Core Circles, and Paul Miller's Protractor. We want to go back to the original topic of relativistic velocity addition as introduced by Albert Einstein in the context of special relativity. We want to look at it a little bit with new eyes in a more geometrical way with these insights that we've developed having to do with core circles and our understanding of Paul Miller's protractor, which we're going to extend a little bit today as well. Okay, so a key theme will be the interplay between our familiar Euclidean geometry, called blue, and this relativistic geometry of Einstein, Lorentz, Minkowski, which we call red. And we've seen that if we're interested in the projective line, namely all the projective one points or lines to the origin, then this core circle with the equation x squared plus y squared equals x helps us. Because in particular, the projective quadrants between two such projective one points turns out to be equal to the Euclidean quadrants between those 2 points. The points where these two lines meet our core circle. And also Paul Miller's protractor applied in this situation. Okay, so it's natural for us to ask, well, what happens in this relativistic setting? Is there some kind of analogous story? And there is. So there's also a core circle in the red setting, which has equation x squared minus y squared equals x. And it looks like a hyperbola as well, like this, but it has center 1/2, 0. And we're going to see that we can ask the same kinds of questions. We can talk about two projective one points, say A and B, and we can try to relate the projective quadrants between these two in this red setting, and this affine quadrants between these corresponding points here, where the two lines actually meet our core circle. All right, so this is a very interesting situation, and it's quite interesting for physicists. So if you're a physics student interested in special relativity, for example, and of course all physics students are, then you're probably going to learn something interesting in this lecture. I'm going to show you a little bit of a more geometrical, algebraic way of thinking about some aspects having to do with velocity addition and relativistic boosts or rotations in this red setting. So let me begin by consolidating some of the things that we've learned in our last few videos. Here is the Euclidean situation again, and we have our two of our favorite projective one points. This one here, which is 3 to 1, call it little a, and this one here, which is 1 to 2, call it little b. And I remind you that if we're interested in where these lines meet the core circle, there's a relatively easy way of doing that. So we take the coordinates here, 3 and 1, and we multiply both of them by the quantity x over x squared plus y squared. So the x squared plus y squared is 10, so we're multiplying both these coordinates by 3 over 10, giving us 9 over 10 and 3 over 10. And that's actually the point A, capital A, on the core circle, which lies on this line. Similarly here for B, we have to multiply by the x coordinate, 1 over the sum of the squares, which is 5. So we multiply by 1/5 to get 1/5, 2/5, and that's the point capital B right there, where this line meets the core circle. Okay, now a crucial fact that we established was that this picture relates the projective quadrants between these two projective one points, namely little q, and the affine quadrants between these points capital A and capital B. And in this case, we've seen probably a number of times now that both of those numbers happen to be 1/2. Okay, so this is a quadrants of 1/2, and this is a projective quadrants of 1/2. And I want to remind you of a few other things in this story. So suppose that we're interested in, for example, this quadrants here. Okay, so the quadrants between O and B Let me write that here, the quadrants between O and B. Well, that's very easy because it's just this thing squared plus this thing squared. So 1/25 plus 4/25 is 5/25, which is 1/5. Okay, and that 1/5 is the same as the point that you get here on the x-axis, which is the vertical projection of the point B. In other words, this 1/5 is the same as the x-coordinate of B. All right, so there's a 1/5 right there. So this is a very lovely fact about the core circle, that if we're interested in quadrants from the origin to any point on this circle, quadrants, then we can obtain that simply by taking whatever point we're interested in, dropping it down, and reading off the coordinate on the x-axis. Very simple. This 1/5 is also, by Paul Miller's protractor idea, the same as this spread that's sitting right there. So this thing is also 1/5. And Paul Miller's protractor is really the point, is that if we want to measure the spread between this line and this line, the easy way of doing it is to see where it meets the core circle and then just drop down perpendicularly, and whatever that x-coordinate is, that's the spread, 1/5 in this case. So similarly, the quadrants between O and A, without any calculation from here to here, will just be the x-coordinate, 9/10. And that will also be the same as the quadrants between the x-axis and this line right here. So I can actually put a little bar there and say that this is 9/10. And we might remark that, what is this spread over here? Well, if this spread is 9/10, then one fact that we know is that this is going to be always perpendicular, because this is Thales' theorem and this is a diameter. So if this is 9/10 here, then this is going to end up being 1/10 over here. And so by the same corresponding fact, the quadrants between A and P is going to be 1/10. Okay, it's the same as the quadrants between the x-axis and our line A. Projective quadrants between those two things. All right, so some pleasant aspects of the geometry of this core circle. Paul Miller's protractor, the fact that spreads in this context are very easy to measure. All what we really need is a linear scale from 0 to 1, and we can read off spreads. As long as we have this core circle in place. We need the circle, but we don't have to have the circle measured off. In particular, we don't have to have an angular measure on that circle. Just the circle as a geometrical object, together with projection down onto the x-axis, is enough to easily read off affine quadrances and also projective quadrances or spreads. All right, so now let's ask another question. Suppose that we're interested in the quadrants between A and B, this number that we've called Q here. So the question is how to read off the quadrants Q, which is the quadrants between A and B, from the diagram. This is not a quadrants where one of the points is O or P. Those kind of quadrants we can read off by the game of projecting down. How do we deal with the more general quadrants between any two points on this core circle? Well, it turns out that there's a nice way of doing that, which extends the idea of Paul Miller's protractor. So let's have a look at how we would actually read that off relatively painlessly with just a little bit of geometry. Okay, so we're going to use a relatively simple theorem from Euclidean geometry, which we'll call the parallel chords theorem. And I'm just going to give it to you here in the case of this core circle, although it easily extends to more general circles. This theorem is almost obvious geometrically, but even obvious things need proofs, and we're going to be giving an algebraic proof of this, so that it's independent of any prior theory of Euclidean geometry. We actually want our mathematics to be independent of Euclidean geometry. Okay, so if O, A, B, and C are 4 points on our core circle C, with O being our usual origin, and OB parallel to CA. So OB is parallel to CA. All right, so these two lines are parallel. Then the quadrants between A and B equals the quadrants between O and C. I hope it's geometrically obvious. But here's the proof. So we're going to let a general point A be 1 over 1 plus t squared, t over 1 plus t squared. We can assume that the point is not the origin. It's a different point. And similarly, we have B in terms of our parameterization of the core circle with a parameter S, and C, same thing with parameter R. So I remind you, this is sort of the generic point on the core circle. It's a rational parameterization of the core circle, which doesn't include the origin O. Right, then the vector from C to A, this vector CA, which is the difference between this point and this point, turns out, if you take these differences and look at what they are, you can write this as a multiple of this vector, the vector r plus t, rt minus 1. And the multiple happens to be r minus t over 1 plus r squared, 1 plus t squared. So please check that. If you just take the difference between these 2 points, you're going to get this vector. The vector OB is simpler because the O is the origin, B is that point there. So we can write that as 1 over 1 plus s squared, take that common factor out, times the vector 1s. All right, so if we're assuming that OB and CA are parallel, well, it means that these two vectors are multiples of each other. And the fact that this is a multiple of that can be expressed by saying that this times this minus this times this equals 0. If you like, the ratio of this to this equals the ratio of this to this. When you cross multiply, there's no more denominators. So r plus t times s minus rt minus 1 times 1 equals 0. So parallel lines imply this relation, and then we can solve this relation for r in terms of t and s. And we get ts plus 1 over t minus s. So if t and s are known, then we can determine r by this formula. All right, and now we can compute that the quadrants between O and C is, well, that's the kind of quadrants that we've just been talking about. Because O is the origin, the quadrants from here to here will just be the x-coordinate of C, which is 1 over 1 plus r squared. And then when you take this r and you plug it into here, and do a little bit of simplification, pleasantly you get s minus t squared over s squared plus 1, t squared plus 1. And that's the same thing as the quadrants between A and B, the quadrants between these 2 points. It's another formula that we established in our last video, or the one before it. The quadrants of 2 points on this core circle. So we've calculated by computation that yes, indeed, if these 2 lines are parallel, then this quadrant here equals this quadrant there. Okay, so now we can use this parallel chords theorem to extend Paul Miller's protractor to allow us to pretty easily read off the projective quadrants between any 2 lines through the origin. In other words, between any 2 projective 1 points. So to find the spread, say Q, or projective quadrants, made by the lines little a and little b through the origin. All right, so we're interested in what is this projective quadrants. We want to be able to read it off. Well, we look at the point capital A and capital B, which are the corresponding points on the core circle corresponding to these lines, little a and little b. Okay, we have these 2 points now. So now we find the point C also on here, so that OB is parallel to OC. In other words, we take the line from O to B, and through A we construct a line parallel to that. That's the red one there. And the other point where it meets the core circle, that's C. And then the quadrants between A and B is what we're interested in, which is Q, and that's the x-coordinate of the point C. In other words, we just drop that point C down onto the x-axis and read off on our linear scale from 0 to 1 what the value is. The x-coordinate of that point C is this projective quadrant's little q. Okay, and why is that? Well, it's just because in this situation here, the parallel chords theorem tells us that the quadrants between A and B is the same as the quadrants between O and C. So if we're interested in this quadrants, which is the same as the projective quadrants between the 2 lines here, this capital Q is the same as this quadrants from here to here. And since this quadrant is starting at O, it's evaluated just by dropping this point down and reading the x-coordinate. So it's very simple. So this way we can easily read off not just projective quadrants from the horizontal to some other point, but in fact any 2 lines emanating from O, and they can be in any direction whatsoever. We just perform the same trick, and we get our quadrants. Now I want to mention just a slight variant on this, which is amusing, maybe 2 slight variants. So the other one is that, well, we didn't have to actually go from O to B, we could also have gone from O to A. Okay? If we had done that, then we would have had to draw a line through B, which is parallel to this one. If we had done that, we would have gotten, that would have been the point C in that case, maybe C prime. And then projecting it onto the x-axis, we would still get exactly that same value there. There's maybe something else to point out, which is also amusing. So another way of getting this point C is to reflect one of these points, say A, in the x-axis, let's say A prime, and then take the line A prime B and a line through O in that direction will meet the core circle in the point C. So you might like to check that those various statements are also true. So there's actually a number of different ways of getting at this point C, or maybe that point C prime, in order to find the quadrants between these 2 points here, or equivalently, the projective quadrants or spread between these 2 lines here. So Paul Miller's protractor is a very flexible and a powerful tool. And remarkably, it works beautifully for other geometries as well, not just the Euclidean one. In particular, it works for the red relativistic geometry just as well. Okay, so let's have a look at the basic setup in the red relativistic geometry. Here is our usual xy plane, and the unit circle in the red setting is x squared minus y squared equals 1. And here it is right here. It's a hyperbola with asymptotes, the lines of slope 1 and minus 1 through the origin. And a very nice object that plays the same role as the x squared plus y squared equals 1 circle in the Euclidean geometry. But in addition, we have something here now that we don't have also in the Euclidean situation, which we might call the negative unit circle. X squared minus y squared equals -1. In the Euclidean geometry, this circle is not so visible as the regular unit circle. It's still important as it turns out, but it's not so visible. Here it's very visible, and it's this hyperbola. It's opening in these opposite directions. Just a rotation of this one by a quarter turn. Right, so what we now want to do is ask, well, what about the core circle? Is there an analog of that? Not surprisingly, there is. It has the equation x squared minus y squared equals x. And you can get at it by taking the unit circle and shrinking it by a factor of 2. In other words, multiplying it by ½. And then translating it over by ½, just the same way we do in the Euclidean case to get the core circle. And here it is here. It now has center, the point 1/2, 0 as before. The asymptotes now are the lines of slope 1 and -1 through 1/2, 0. And it has one branch going through the origin O and another branch going through this point P. The other thing we need to know about it is how to find a point on it that's lying on a given line. So if we have this line, or projective 1 point, say A, with coordinates u to t, that means that the point ut is actually somewhere on here, but this is only determined up to a scalar. Then a corresponding point on this line which actually passes through the core circle is this point A, which is u squared over u squared minus t squared and ut over u squared minus t squared. You see that is a multiple of ut. If we take the u and u squared minus t squared out front, it's a multiple. And it's easy to check that if you take this thing squared and you subtract this thing squared, then you do get the x coordinate. So this is very similar to the story in the Euclidean case. We have to take u and t and multiply both coordinates by the x coordinate u divided by u squared minus t squared, the quadrants of that point in this red setting. So it's very analogous to what happens in the Euclidean situation. Okay, now I want to show you that the core circle in this relativistic red setting really plays the same role, is just as useful for physics-minded people as our Euclidean core circle was in the Euclidean case. Okay, so let's make a few calculations, and I'm going to use specific points, and I'm going to leave you to generalize these things for the general case. So here's our core circle through the origin and through this point P, interval 0, 1 right there. Center 1/2, 0, asymptotes like this. And we're going to choose two projective 1 points. Little a, which is 4 to 3, and little b, which is 5 to 1. The corresponding points on the core circle are capital A, which is 16 over 7, 12 over 7. How did we get that? We multiplied both of these coordinates by x over 4 squared minus 3 squared, which is 7. And the corresponding point on little b is this capital B, which is 25 over 24, 5 over 24, obtained from this one by multiplying both coordinates by the x coordinate divided by 5 squared minus 1 squared, or 24. So we have to multiply by 5 over 24, getting 25 over 24 and 5 over 24. So let's illustrate a few things. First of all, the quadrants between these two lines, projective quadrants between this line little a and this line little b, or the spread, if you like, but in this red setting. So it's the projective quadrants between 5, 1 and 4, 3, and that's 1 minus. Basic formula is to take the dot product between these two things. So 5 times 4 minus 1 times 3, because it's the red dot product or inner product. So all of that squared divided by 25 minus 1 times 16 minus 9, the difference of the squares. And that simplifies to be minus 121 over 168. And we've seen that before because we've had a look at these two particular lines previously. What about the ordinary affine quadrants between these 2 points, still in the red setting. So now it's just a question of taking these points, taking the difference between the x-coordinates squared minus the difference in the y-coordinates squared, and that turns out to be minus 121 over 168, which of course is exactly the same as this projective quadrants. So the story is exactly the same as it was in the Euclidean setting. The projective quadrants between these 2 projective 1 points is the same as the affine quadrants between the corresponding points on the core circle. Very pleasantly. So we can go from affine quadrants to projective quadrants very easily by this intermediary of this core circle. Now what about this Paul Miller's protractor story? How do we actually read off what this quadrant is, or maybe what this projective quadrant's Q is? Well, we have to find the point C. There's the line OB. We take the line through A, which is parallel to this one, something like that, and see where it meets the core circle. That will be the point C. And how do we find that? Well, we just take that vector there and go a multiple of that vector from A, see where we meet this core circle. Another way would be to reflect A in here, say A prime, take A prime B, that vector, and move it to O, and see where that line meets the core circle. Either way, you can calculate that the coordinates of C are minus 121 over 168 and 187, 168. And lo and behold, when we project this thing down, the number that we get there is minus 121 over 168. Exactly the number that we're looking for, exactly the projective quadrants between the 2 original lines, or equivalently, the affine quadrants between these corresponding points on the core circle. So Paul Miller's protractor is working very well for us here. And not only can we find quadrants between the horizontal and an arbitrary line, that would just be the case when this point B is actually P, just a special case. But we can in fact find the projective quadrants between any 2 lines to the origin. So we can easily find spreads using this basic setup. Basically just draw a few parallel lines, drop down the x-axis, and read off a value. And notice that the values that you're going to read off are necessarily numbers which are less than or equal to 0, or numbers which are greater than or equal to 1. Because this hyperbola, its shadow on the x-axis, is just these segments here. In particular, this segment here doesn't get covered. So you're never going to get a projective quadrants with values strictly between 0 and 1. That's the Euclidean case. The Euclidean case is giving us values in here. This relativistic case is giving us values outside the interval. They complement each other in a pleasant way. Okay, you'll like to generalize this. So I've done it with a special case. It's a lovely exercise in algebra. Basically very similar to what we did in the Euclidean case. Just to work it out with general points, work out the algebra, see that everything works out pleasantly as it should. Okay, so now I'd like to go full circle and go back to the original idea that we started talking about with relativistic velocity addition of Einstein. This formula that if you have 2 relativistic velocities, say 1/5 and 1/2, then to add them relativistically, we don't just take their sum, we take their sum divided by an appropriate sort of scaling factor, which is 1 plus their product. So 1 plus 1/5 times 1/2. So this is altogether 7 over 11. It's a number that we've seen before because we've actually looked at these particular examples before. So what I want to show you now is sort of to illustrate how this relativistic velocity addition actually has a very pleasant geometrical interpretation, very much along the same lines of the kinds of things we've been talking about. So here's our core circle, and these two velocities are represented in this picture by two lines. There's the line 5 to 1, and there's a line 2 to 1. Now, with this particular picture that we're drawing here, we're thinking of sort of time as being in this direction, a little bit different from what relativistic physicists usually do, but more in keeping with the usual idea about describing a particle's trajectory by having time here and position here. Okay, so this represents a velocity of basically 1/5. If we renormalize this to be 1 to 1/5, namely that number there be 1/5, then that's giving us the velocity. And this is a bigger velocity. It would correspond to, that's 1/2. If we divide it by 2, we get the point 1 to 1/2. Okay, so what's going on here? Well, it turns out that something's interesting. So first of all, let's call this line B and this line C, and the corresponding points on the core circle are capital B, which is 25 over 24, 5 over 24, and the corresponding point here is capital C, which is 4/3, 2/3. Okay, there's the point B, there's the point C. Now what I'm going to do is I'm going to look at this corresponding sum, the relativistic sum of the two velocities, 7/11, which corresponds to a line like this with name 11 to 7. And the corresponding point on the core circle would be 121 over 72, 77 over 72. We get that by multiplying both coordinates by x divided by 11 squared minus 7 squared. 11 squared minus 7 squared is 72. So we have to multiply this by 11 over 72. That's how we get this point right here, and there it is right there. So I want to explain that basically the same picture that we've just been looking at suffices to show there's a geometrical relationship between these 4 points. P, this point B, this point C, and this point D. And we can see that by just looking at the vector from B to C. B to C, it's just taking the difference between this point here and this point here. Okay, so that minus that gives the vector 7 over 24, 11 over 24. That's the vector from capital B to capital C. While the vector P to D, it's the difference between this point and the point P, which is, of course, 1, 0. And you can work that out easily enough. That's 49 over 72, 77 over 72. And then when we look at these two vectors, we notice that they are parallel. They're both multiples of 7, 11. Take out common factors. This is 7 to 11. This is 7 to 11. So telling us that the line BC is parallel to the line PD. This gives us a geometrical construction for Einstein's relativistic velocity addition. If we started with this line representing a velocity of 1/5 and this line representing a velocity of 1/2, and we were interested in what is the velocity corresponding to their relativistic sum. We don't, in fact, have to do any algebra. We don't even need to know any of the coordinates. As long as we have the core circle in front of us, we just look to see where our two lines meet the core circle and draw a line through P which is parallel to that segment, and where that line meets the core circle the second time, that is the point that we're interested in. That then is the velocity, which is the relativistic sum of the two original velocities. So this is related to an interesting multiplication or group structure on a general conic, in fact, which is described in Algebraic Topology 2, and I give some references there to other people's work as well. So there's a general story here. This is just a sort of special case of some phenomena that happens quite generally for a general conic. But what we're seeing is that this perhaps somewhat mysterious relativistic addition formula of Einstein geometrically is a very, very simple thing. It's really sort of a manifestation of the parallel chord theorem for our core circle. So let's summarize what we've been doing, and especially noting the parallel between the Euclidean situation and the relativistic one. That we basically have a way of looking at these things where there's a bit of algebraic difference, but the essential content algebraically is really the same in both of these different directions. So here is our core circle again, now in the Euclidean situation, so we're working in blue geometry here. And suppose that we have 2 points A and B on the core circle, and they have the same kind of formulas as we were talking about before. So A is 1 over 1 plus t squared, t over 1 plus t squared. That is, it's the place where the line through the point 1t meets the core circle. And B is the place on the core circle where this line 1 to s meets the core circle. It's got coordinates 1 over 1 plus s squared and s over 1 plus s squared. And let's also suppose that we have a third point D given by 1 over 1 plus p squared, p over 1 plus p squared, so that it's the point on the core circle, such that this line goes through our x equals 1 line at the point 1p. So on this line here, these three lines have very simple intersections, 1 comma t, 1 comma s, and 1 comma p. And now let's suppose that in addition we have a similar kind of parallel situation as we did in the earlier examples, but slightly different. That we assume that AB is parallel to PD, where P as before is our point 1, 0. So imagine starting with AB, drawing that line segment there, and then drawing a line through P, which is parallel to that, and seeing where the second point of intersection with the core circle is, and calling that D. Then the claim is that this number P is obtained from T and S through this relation, that 1 to T times 1 to S equals 1 to P. And here I'm using the algebraic structure on the Euclidean projective line that we talked about a few videos back. I remind you that in general that goes, we take this times this minus this times this. That's the first entry. And then the second entry is this times this plus this times this. So it's just the one-dimensional or projective version of complex number multiplication. And that this arrangement between T, S, and P is equivalent to this formula for P in terms of T and S. Namely, P equals T plus S over 1 minus TS. So this is how the multiplication, the one-dimensional multiplication on our projective line translates when we're looking at things in terms of the meet on this line here. This is the kind of thing that we've seen before, but it directly connects the multiplication or algebraic structure on our projective line with rotations in the plane or on the core circle C. And this algebraic structure, where we say this times this equals this, really corresponds to addition of angles in the transcendental classical setting, but there's no real need for angles here. So in a classical setting, you would say that this angle plus this angle equals this angle. But we're able to express this fundamental relation purely algebraically without having to need these transcendental notions of angles. And I'd like to point out also a secondary kind of activity to think about. Suppose that we look not just at the core circle, but also at the unit circle centered at 0, 0. So the unit circle, let's draw it in red to distinguish it. It's going to be this bigger circle, something like this, coming out like that, right? So the unit circle going around like that. So you can convince yourself that, in fact, the same kinds of relations hold here. That if these two lines meet the unit circle, let me put them at those points there, and meets also this thing here, then you can verify that, in fact, the relation here, this line segment here, and this line segment here are also parallel. So whether we're measuring the rotations on the core circle or the rotations on the unit circle, it's really equivalent. But with the proviso that on the core circle, things are actually making sense at all times, because we don't have to worry about whether a line through the origin meets the core circle or not. It always does. Okay? That's not necessarily the case for the unit circle, because sometimes a line through the center will meet it and sometimes it won't. So the core circle is a much better way of connecting the projective line with the geometry and the algebraic structure of the plane. All right, now let's look at the same thing, parallel situation in the red geometry, which connects to the Einstein relativistic addition of velocities, and rotations in the hyperbolic setting, so-called Lorentz boosts. So here is our red geometry, and here is our core circle in the red geometry, x squared minus y squared equals x, going through the origin 0 and also this point P here. Okay, so the exercise now is very analogous to the previous one. This is the point, that these two things are basically the same algebraically, almost. And even though the diagrams look very different. Once you understand the way one of them works, understanding the other one is a very simple step. Okay, so suppose that we have three lines through the origin, and they meet this vertical line where the x-axis has coordinate 1 at the points 1, t, 1, s, and 1, p, just as before. And that these three lines meet our core circle at points A, B, and D. So that A is 1 over 1 minus t squared, t over 1 minus t squared. B is 1 over 1 minus s squared, s over 1 minus s squared. And D is 1 over 1 minus p squared, p over 1 minus p squared. And let's assume, in addition, that they're related by this following geometrical condition. That the segment AB, the line AB, is in fact parallel to the line PD. This is P. So exactly the same condition as we just had on the previous thing. So show that the relationship between the three projective lines is that this projective line times this projective line equals this projective line, in the sense of the algebraic structure in the red geometry, which I remind you, here's the formula for that, that A to B times C to D is AC plus BD times AD plus BC. So almost the same as the Euclidean situation, except that there's a plus sign there, not a minus sign. So that this parallel business on the core circle exactly corresponds to having this multiplicative relation in this one-dimensional projective line. And then show that equivalently, this just unravels to showing that P equals T plus S over 1 plus Ts. In other words, our relativistic addition formula. So we see a lot of things connecting here. We see that this Einstein relativistic addition of velocities is really a one-dimensional phenomena at heart. Okay? It's really a story that's describable just in terms of this one-dimensional projective situation where we have this algebraic structure on the this one-dimensional situation coming from this red geometry. And that when we transform that situation to the plane via this core circle, then we get this very nice situation that we can sort of read off what's going on purely in terms of these kind of parallel chord kind of situations. That chord parallel to that chord. If you're interested in this kind of alternate red kind of geometry, you might have a look at some of the later videos in the Wildland Alge series, so roughly from 33 to 42, where I talk about some physics-oriented things, including relativistic physics, and also talking about the kinds of alternate complex number structures that are going on here. Okay. So it certainly suggests that there's a red version of complex numbers, where this is the basic formula, instead of having a minus sign like we're all familiar with ordinary complex numbers. So it turns out that this red complex number situation is essentially just as interesting as the usual complex number story. Okay. We start to see that our focus on the Euclidean situation, which is largely driven, first of all, by the historical dominance of Euclid, but also strongly supported by our reliance, our over-reliance, on real numbers and distances, angles, circular functions, cosine and sine, their inverse functions, and so on. All these transcendental things, that they box us in and prevent us from seeing the obvious parallels between the Euclidean situation and this relativistic situation. When we let go of the real number scaffolding and move to a purely algebraic rational point of view that works over a general field, we see that the two stories are pretty well the same. We have the language to be able to see things in a much bigger way. And then it turns out that as one goes a little bit further in mathematics and go to higher dimensional things, that this relativistic kind of mathematics that we've touched base with here turns out ultimately to be, in fact, more important than the Euclidean one. Okay. So it turns out that when you move to sort of matrix algebra, operator algebras, to functional analysis, to Lie theory, and to a lot of projective geometry, that the relativistic generalizations of what we've been talking about figure more prominently than the Euclidean generalizations. So it's a very good idea, if we're interested in higher mathematics, to really fully understand and appreciate the parallel between these two kinds of geometry, and the fact that the red geometry is every bit as interesting and important as the much more familiar blue one. All right, so lots of important ideas and interesting kinds of things to think about here. In our next video, we're going to return to this projective triple quad formula, also known as the triple spread formula in the two-dimensional situation, and show how it connects with circumcircles of triangles, and actually gives us a very powerful tool to address the issue of curvature in the plane. Usually a calculus notion, but we'll see that with our algebraic tools at hand, we can get at curvature in a much more elementary and, in fact, pleasant way. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.